So we have seen till now how charges are affecting some other third charge, right? Nth charge. Say this is Q naught. This can be pushed around by Q1, Q2, Q3, Qn in any manner. But not all the time our distribution will be so. What I mean is, need not have the charge in this manner. We need not get a chance to tell, you know what, first charge is over here, second charge is over there, so on and so forth. We can have charges that is spread across or lengths or area or volume. That is, the charges are so spread across, right? We are not able to differentiate the first charge and the second charge, not to a scale which we are living in, right? If you, of course, if you zoom in, if you go to the electron space and dive down to that 10 to the power of minus 19 size and all of that, right? Maybe then it makes sense, but not at human scale. We might not be able to differentiate that there's a charge over there, next to that there is another charge. It might not make sense, but still they are charges. Still they will affect this Q naught, which is over here. It can be either a pull or a push. Such a scenario is your continuous charge distribution. So the basic idea of the word continuous charge distribution is that the charges are spread across continuously over length, area or volume. It can be a wire, it can be a plate, it can be anything and everything. Okay, now the question is, how will we study this? That's what we're going to study from now. So we are diving into the next version of charges, wherein charges are not pinpointed here and there, but they are spread across in certain space, right? So how will we handle this? By dividing them into smaller parts and then adding them up. Again, remember, adding them how? With the help of superposition theorem. Again, remember that these two are charges. These two will behave or will have the similar property or same property, not similar, same property as this. Whatever math we did over here is again applicable over here also, but the scale is small, right? The scale is small. So what do we use whenever the scale is small? Yes, we will use, think about it, correct, differentiation and integration. So we will consider very small charges and very small forces, right? We'll see how they behave. And then what do? We add them up. So what does very small charges mean? It means that we have a charge, right, wherein it is very small. This is what it is. TQ is nothing but a very small scenario wherein the charge, the amount of charge is almost approaching zero. This is one of the ways of representing. Okay, and this produces a force dF. And once we know dF, we can find F by what? By integrating. Okay, guys, integration is nothing but adding. It's a fancy way of telling, let's add up. Let's add up a particular function behaving in a particular way. Is it not? Okay. So let me put it officially. The common approach to find the force and of course thus your electrical field by a continuous charge distribution is the following. We need to start off with a statement that ignoring quantum nature, imagining a continuous charge distribution consisting of a large number of small charges dq. You guys understood what is dq, right? So we have, say, a cloud of charge, right? I'm going to consider a very small set of charge, and this is q naught, somewhere which is along this length, and say this is r pushing in the direction of r cap, the force of df, right? So df will also behave the same way. K q naught dq by r square vectorially, it will be of this manner, as simple as that. Now, what is the total effect of all of this? Well, we will have to add it up. Okay, so that will be your total force. So integration of K q naught dq by r square, right? Again, these are charges, product of charges, r cap, that's your direction. Now, what is fixed and what is going to vary? That's important for you guys to observe. Very important key over here is to understand what remains constant and what varies, and how it varies. And how it varies. This is the key. So yeah, you guys can take a second and think what might remain constant and what will vary. You guys decided? K by default is a constant. Q naught is a constant. R square is also constant, right? No, R square is not a constant. R square, right over here, if this is the dq, this will be different, right? The length, the distance will be different. So R square is over here. Obviously, the direction will also change, is it not? And not all the places dq will remain the same. This is what the entire chapter is about, the other half, that is. To understand what is constant and what varies and how it varies. If you are able to express all of this with a single term, right? Single variable, your job is done. That's the entire job over here. Expressing that in single variable and integrating. Okay, yes. So what is that we learned now? We can have bunch of charges that can be spread out in this manner, but not all the scenarios also. In our real life, charges are spread out in a weird manner on different lengths, areas, and volume. The effect of this can be understood with the help of simple superposition theorem only. But here the size with which we are playing with is very small, right? So we need to make use of the concept of integration and differentiation. And when we talk about integration and differentiation, we have df and the variables related to df. And we have certain variables that will not remain constant, right? With the change of dq and r and so on and so forth, things will change. And expressing this as a single variable and integrating, that's our job. Okay, so we will understand throughout the next half of the syllabus. For now, you guys have to pause, have a look, and write everything.